In this talk, I'll be giving you some tips, some tricks, and some tools regarding performance. You've probably heard this line before. Flutter is fast by default and you don't need to worry about performance. This is true for the most part, and it is important for me to note that you should not be pre-optimizing your application when not needed. But understanding what can cause your app to be slow, and more importantly, how Flutter's rendering works underneath the widget you use, will level you up as a Flutter dev. A quick intro. My name is Gordon. I work at Stream as a Flutter developer advocate, and I also have a YouTube channel called Fun with Flutter that, you guessed it, covers Flutter topics. I hope you learn a few things from this talk because I've wasted so much time in the past not using the correct tool for the job. So don't leave. I know this looks boring, but I promise that this talk will get a lot more interesting, and I'm actually going to go over the fundamentals quite fast. So first, let's take a look at the different phases that are responsible for rendering. We can see that we have the build, layout, and paint phase, and then finally all of this creates a display list that will then be rasterized by the GPU. So the GPU will display this as an image that can be rendered to the screen. The build phase is what we as Flutter developers are responsible for. This is the rendering phase that we control the most, as this is where our widgets get rebuilt and the subsequent elements for those widgets get inflated, and from those widgets we also create the relevant render objects. Then we head into the layout and the paint phase, and the framework or the render objects, they manage this, and we generally do not need to worry about laying out and painting. You have the option to create your own render objects, of course, or you can always manage custom painting through a custom painter. So let's break these phases into the well-known Flutter trees. There are 3 trees: the widget, element, and render tree. And we will use a simple example to illustrate how these 3 trees work together. We have a widget called myWidget that returns a red container. And as you can see, Flutter builds out our tree. The interesting bit at this point is that there is another widget added automatically called a colored box. In the element tree, you will note that we have a component element and a render object element. And then finally, we have a render colored box in the render tree, the only thing in our render tree at the moment. Flutter created everything to the left to finally have this one render object. This is the core of the rendering library. This class implements the basic layout and painting protocols. You can think of elements as the glue between our widgets and the render objects. They keep track of parent and child relationships, and they also manage the state of our widgets. They determine when a render object should be updated or recreated. This is another way that we can represent the tree. You can see the stateless widgets and the stateless elements. Okay, so really interesting, but why should we care? Let's go back to our example. We'll change my widget to now be a stateful widget instead, and then add a gesture detector. When clicked, it calls the method changeColor, which sets the state and changes the color from red to blue. The darker nodes are those that were added or changed. As you can see, the trees are now starting to grow, and it's already getting complicated. The question now though is, what happens when we tap the gesture detector? How does Flutter efficiently change the color of the container without doing unnecessary work? Well, this is where the whole concept of these different trees come into play. The widget tree is designed to be torn down and recreated a lot. Widgets are meant to be lightweight blueprints used by the elements and the render objects. While widgets can be recreated a lot, the associated elements and render objects are reused as much as possible. To put it more simply, widgets are immutable and render objects are mutable. Something that is extremely important to take note of is the fact that Flutter can determine what element and render object it can and can't reuse by checking to make sure that the type of the widget has not changed. For example, if we rebuild the widget tree and all we change in the tree is my widget with some other widget, for example, a widget called exact same different name, then that will cause a Flutter to recreate all of the elements and render objects for that part of the tree, even though all of the widgets lower in the tree are still the exact same. Okay, we did it. We got through the theory. Now let's actually get to the fun part and explore the tools and examples. And to begin, we will explore the build phase a bit more. And by a bit, I mean a lot. To explore that, let's take a look at a tool that allows us to track widget rebuilds. The Track Widget Rebuilds option in IntelliJ and Android Studio allows you to do as the name says. As you can see, when we call setState, it rebuilds my widget and all of the widgets in that build method. This tool is particularly helpful when you're doing animations or working with lists or anything more complicated than a simple example like this. 10 out of 10 recommended tool. Actually, all of the tools are 10 out of 10, so we can get that out of the way. Next up is the profiling timeline in DevTools. We can use the timeline in DevTools to identify unnecessary rebuilds, but that's not what this is truly useful for. The timeline is meant to identify frames in your application that are expensive to compute. But if you enable enhanced tracking and track widget builds, then you will see all of the widget build methods that were invoked for each frame. Important to note that the time it takes to complete a frame is important. If it takes too long, then that will cause jank in your application. The red frames you can see at the top left indicate jank in the timeline. If you're a gamer, this will be more familiar to you. It means that the application drops frames and causes a stutter. If you drop too many and it becomes noticeable, people will complain. Flutter aims for 60 frames per second, and that is considered good for mobile. Your eyes won't be able to noticeably pick up a delay between frames. Normally Flutter does 60 frames per second without issues, except when it doesn't. If we go back to our previous example of the different rendering phases, we can actually take note which is the UI thread and which is the raster thread. You'll note that these match up nicely with what we see on the timeline. The general rule is that if the UI thread is slow, then you made a boo-boo somewhere in your widgets or state handling. This is the code that you wrote and code executed by Flutter's framework on your app's behalf. The UI thread creates a layer tree, which is basically a series of painting commands, and sends the layer tree to the raster thread to be then rendered on the device. If the raster thread takes the raster thread then takes the layer tree and displays it by talking to the GPU. If the raster thread is slow, then it can unfortunately mean a lot of different things. Most likely you still made a boo-boo somewhere, or you're trying to do something too graphically complex. Flutter uses Skia for its graphical rendering. We will take a deeper look at this later on. You can easily see an overview of your app's performance by enabling the performance overlay. For this overlay to work, you need a material app widget in the tree. This will show you a real-time view on the device of how long each frame takes, so you can use your application and identify areas that are causing jank. While we are talking about different threads, it's worth mentioning isolates. Isolates are like threads or processes, but each isolate has its own memory and a single thread running an event loop. Unfortunately, we don't have the time to delve deeper into this topic, but if you're doing any long-running operation in your Dart code, then it could be a good candidate for isolates. Dart has also recently released something called isolate groups that enable you to spawn multiple isolates that live in the same group. Isolate groups enable performance optimization, such as code or sharing code. I recommend this video on the topic if you're interested to learn more. There are also 3 different Flutter build modes that you should take note of. Each has their own use. The architecture between debug and a profile or release mode build is completely different. Dart does a lot of optimizations for a release and a profile build. For example, compiling ahead of time instead of just in time, tree shaking, null safety, and removing unneeded code and checks. Release mode should be the fastest, as most of the tracing is also then removed. If you want to go beyond just seeing what widgets get rebuilt and repainted, and you want to analyze how long the build time of each frame and widget is, then you will need to run in profile mode. You can also you can only run profile mode on a real device. Okay, we've explored quite a bit. Now the real question is, how do we reduce widget build cost? The first thing you should take note, should always do, is make use of constant widgets whenever possible. A const variable is a compile time constant, which means a single const object will be created and reused no matter how many times the constant expressions are evaluated. For widgets, this also means that Flutter won't unnecessarily rebuild widgets marked as constant. Flutter will be smart about determining that the widget's build will not have changed, so it can actually skip rebuilding it. To get this compile time optimization, we will actually need to build for profile or for release mode. This doesn't just apply for widgets though, but for any object. In this example, we have a for loop iterating from 0 to 100, and we're creating an object called const object and const object not. One is constant and the other is not. As you can see, if we inspect our memory, we have a single instance of the const object and 100 of const object not. So always prefer const. When it makes sense, you can also use static for non-constant objects when the class can't be constant, but you only need a single instance between all of your objects. Both of these classes are not constant, and we create 100 instances of the const object not class. Inside that class, we create a static final of const object another not, and inside the constructor, we print that static object. This will still create 100 const object not instances, but only a single const object another not. Sorry about the naming. You can also be clever in the way that you do your execution. If it's not necessary to compute something, then don't. So let's take a look at a simple example. Here we can see we have a simple condition and two expensive operations. If the condition is true, only then will we call the first expensive operation, and only if that is also true will we call the second. If the first condition was false, we will never call the expensive operations, and as a result, we saved on our compute costs. We can also sometimes increase the readability by using the late keyword. This example is exactly the same as before, but take note that operation 1 and operation 2 will only call the expensive operations once we try to access them, because of the late keyword. This is referred to as lazy computation. A big shout out to Remy for inspiring this example. Definitely follow Remy on Twitter. I have learned a lot from him. Back to widgets. The next important thing to reduce our widget build cost is to prefer small widgets. The main benefit is that it reduces the widgets that need to be to rebuild when calling setState. It also makes testing easier. Here we have the good old counter example. When you press the floating action button, it calls setState, which causes all of the widgets in my homepage to rebuild, except for those that are constant. So this is maybe even an example that we can break it down into smaller widgets. Can you think of a better way to do this though? To avoid all of these widgets rebuilding unnecessarily? You guessed it, the answer is state management. The state management frameworks we have are amazing, and all of them have their own ways to reduce widget rebuilds in your application. But let's not argue over our favorite state management solution. We'll keep it simple. Back to the counter example, let's unnecessarily optimize this like the developers we are. As you can see, we're using a plain old value notifier and value listenable builder. Now only the floating action button and the text will rebuild when the button is pressed. There are many other ways we could have done this as well. Was that necessary? Definitely not. We basically overcomplicated it and overthought something that didn't need to happen. But the principles remain, and it's always important to keep your widget rebuilds in mind, and it also doesn't hurt to have the extra performance. Next up, what should you prefer, creating widgets or creating helper methods? I'll give you some time to look at the code and to give your opinion in the comments. Just quickly looking at the code though, it seems like using helper methods would be the faster approach. So what do you think? But there's actually no competition. We've indirectly touched on the points why you should prefer dedicated widgets. The main reason is that when we call setState or rebuild a particular widget, we want to contain that to only rebuild what is needed. This becomes really hard to do with helper methods. Our builds become really big as a result of using them. If you want more info, this is a great video on the topic. Okay, last thing about widgets. We've covered quite a bit regarding them, but this is the last thing and probably the most important. Don't do expensive work inside your build. It's the fundamental thing you should probably take from this talk. We've seen and talked about the fact that widgets are just blueprints for render objects and that Flutter recreates them a lot, so keep them small and keep them lightweight. In this example, we are removing the call to really expensive operation from outside the build to inside the state class. We can be smart about taking expensive work out from the build and putting them in our state instead. And Flutter can recreate the widgets as much as it wants without recomputing the expensive operations. Doing this in stateful widgets sometimes gets hard to manage. So this leads us back to state management. Yeah, you guessed it. So you should abstract complicated logic out from your widgets to your state management of choice, and be sure to reuse as much logic and not to redo any work when not necessary. Now let's move on to another area of the rendering phase that we can help control, the paint phase. As we've talked about before, a widget's painting is managed by the associated render object. You normally do not have to think about this step at all, but you should consider it from a performance perspective. Let's take a look at a practical example. We have our normal My widget that we've used before, but now it's sitting in a stack on top of a custom paint that paints something called Expensive Painter. As you can see, it's a rather complex painting, and intuitively you might think that Flutter paints that expensive painter once, and only repaints My widget when it updates. Actually, no, it does not. In this video, you'll see that even though only the My widget is being updated, the entire stack is being repainted. And the reason for that is because Flutter actually repaints everything on screen, each frame, unless you tell it not to. You can also see that both the UI and raster threads are working really hard. Note that this is on a profile release on a real device. We can easily solve this by introducing a repaint boundary. This widget creates a separate display list for its child, which can improve performance if the subtree repaints at different times than the surrounding parts of the tree. A render object will repaint whenever any render object that shares the same layer is marked as being dirty and needing paint. With the repaint boundary, now you'll see that in our paint phase, we are only repainting the colored box and not the expensive painter. Also, after a couple frames, the engine decides that it's worth it to cache the image, and subsequent raster thread frames complete faster. The dark red bar in the third frame actually indicates shader compilation time. So, repaint boundary, everything, right? Not really. A repaint boundary basically instructs Flutter to cache the image, and raster cache entries are expensive to construct and takes up a lot of GPU memory, so only cache images when necessary. You can also see some metrics on your repaint boundary. In this example, it says that it's an outstandingly useful repaint boundary. You can also see which images are being cached by enabling the checkerboard raster cache images flag. Run the app and look for images rendered with a randomly colored checkerboard, indicating that the image is being cached. The checkerboard images should remain constant. You don't want to see any flickering, which would indicate that the image is being recached. I made a video about this if you want to explore the topic deeper. Highlight repaints, a fantastic tool to easily observe repaints in your application. This will basically show you the different repaint boundaries in your app, and it's awesome. Fun fact, Flutter automatically adds repaint boundaries to items in a list. When you highlight the repaints, you can see the different repaint boundaries. If you were to add something to the bottom of the list, none of these render objects will repaint. Using this tool helps us at Stream to observe weird behavior in Stream Chat Flutter, where if the list is in reverse order and new items are added to the top, then everything repaints. The elements and render objects are recreated, which means you also lose access to the state. There's a way you can help Flutter to determine the new position of items in a list so that it doesn't need to repaint and recreate the widget. As you can see here, the colors stay consistent. We made a video all about this on our Stream Developer channel that you can watch. Let's jump back to our well-known container example. Take a look at the following code. What do you think will be the output? What color do you expect? I will give you a few seconds to type it in the comment section. Okay, the answer is red. So correct to those that got it. Congratulations. Let's actually delve deeper into what is happening at the Skia painting level. To illustrate the painting instructions that we send to Skia, we will run our application in profile mode and then use the Flutter screenshot command to capture a Skia screenshot. Then we'll go to the Skia debugger and load the file the previous command generated. At debugger Skia, I'll load the Skia file and then we will inspect the instructions. This is what happens in the raster thread layer where Skia runs. As you can see, we create our red container with draw rect instruction. Now back to our example, we'll change it slightly. We'll add another container, this time a blue one above the red container. And again, tell us in the comments what will the color be. Correct, it's still red. But if we take a look at the painting instructions in Skia, you can see that we still go through the process of painting the blue rectangle. Flutter and Skia is unfortunately not that smart to optimize that out on your behalf. Something to keep in mind when you do more complex painting. There may be times when it makes sense to not render something when it's something else, or when something else obscures it, given that that something is complex to render. Back to the code. Let's make it a bit more complicated and add an opacity with 0.5 between the two containers. And again, what will the color be? You have 2 seconds. Correct, it's 8B6094 in hex. Congratulations to those that got it correct. I promise there is a point to this. If we look at the Skia debugger, there are quite a few more instructions. Most notably is this call to save layer. This bad boy is something we should pay attention to. Calling save layer allocates an off-screen buffer. Drawing content to the off-screen buffer might trigger render target switches that are particularly slow in all the GPUs. Basically, that means you should try to avoid it when necessary, or when you can. There are a few things that could cause a call to save layer, and generally some rules you need to think about. Use opacity only when necessary, and clipping can cause save layer when you use the anti-alias with save layer clip call. Other type of clipping is not as expensive as opacity, but it is still costly. So you're telling me I can't use opacity and clipping? No, don't worry. There's 100% of the time, 80% of the time, a way around it. Back to our example, let's modify it. So we remove the opacity widget and instead set the color, the opacity and the color. And as you can see, now the call to save layer has been removed and order has been restored. Let's take a bit more practical approach and look at a real-world example. I made a demo application using the StreamChat SDK and Rive to create a sample chat app that allows you to send animated stickers. If you're interested, we created a code lab showing you how to create this app. Checkerboard off-screen layer. This is a switch that you can enable in your application to check whether your app is using save layer. Once the switch is enabled, run your app and look for any images that are outlined with a flickering box. The box flickers from frame to frame if a new frame is being rendered. Now in this video, we will turn on checkerboard off-screen layer to true and we navigate in the app. You will see randomly colored checkerboards whenever we do more complicated effects. This is a nice switch to turn on to identify areas in your application that are calling save layer and may prompt you to do further investigation. However, just because it's showing doesn't necessarily mean it's bad. Just be mindful about it. If all of this is not enough, you can also enable the trace Skia flag when you run in profile mode. This will give you even more info. An interesting tool is the more debugging options that you can only run in debug mode. This allows you to disable certain effects in your application so that you can see if it has an impact on performance. I believe this is a fairly new tool. Another awesome tool in DevTools is the highlight oversized images. This tool will revert images that are too big and that are using too much memory for the size they're taking up on screen. These images that I'm using in this example should be replaced with smaller images. And as we're reaching the slide, I'm noticing that we are running out of time. So I'm just quickly going to go over these slides, just skim through them. The main point that I'm trying to make though is that don't be too scared. You can still use Flutter normally. Just be mindful, and there's always a better way to do something. So definitely read the documentation and beware of some of the gotchas, the widgets that could cause a lot of computation time. And you can always cache widgets. Animated Builder is a good example. And yeah, like I said, don't be too careful. Take a look at this slide later on. And then, yeah, if you want to take a look at anything Philip has made, he has made awesome blog posts and videos on this topic as well. Any questions, please feel free to ask.